Peter Jan van Leuven, who will introduce Michael to the audience. Thank you very much.
Okay, so Michael, it's an absolute honor to introduce you. So Michael is a distinguished research professor at UCLA and also a distinguished professor at the Ecole Normale Supérieure in Paris. So so that already gives you some idea. So he's born in Hungary, so he speaks Hungarian, and that's probably one of the reasons why he speaks so many other languages too. My last count, I think, is 14. Probably it's more by now. But the point is that he can probably address each of you in the audience in your own language. Now, he got his PhD in '75 in the Courant Institute under the supervision of Peter Lex, who later won the Able Prize in 2005. And his thesis was on well, theoretical climate dynamics. Let's put it. Let's call it that. And that sort of set the scene. And in '85, he became the full professor at UCLA, indeed in theoretical climate dynamics. And so what his contribution to the field are so many and so broad. Yeah, it's actually in a sense unbelievable. And maybe I can summarize it by using chaos theory and dynamical system theory and apply these to the climate problems, and at the same time, because the climate problem is such a complex problem, developing these methodologies further. And of course, he also worked on data simulation, and that's why he's here. And there's of course a connection between chaos and dynamical systems and data simulation. And so I recall his 81 paper on extended camera filter and his review paper with Paola Magnetosphere in 1991 in Advances of Geosciences. That was probably the first review paper in data simulation, and it's still a very good read. So Michael has been an outstanding scientist, of course, and he also shaped the field by being director of several institutes, head departments, etc. Again, too many positions to mention here. And he has won many awards and many honors. I just name a few again. He's honorary member of the EGU, of the Hungarian Academy of Sciences, of the Romanian Academy of Sciences, of the Royal Astronomical Society. He has won the Richardson Medal of the EGU, but also the Wegener Medal at the EGU. He's a Union Fellow of the AGU and many more, right? It just doesn't stop. And for the young and old under us, this guy sets a very high bar in number of publications, right? It's over 350 now, and it just keeps going. Books, book chapters, and indeed he is one of the highly cited researchers in the Web of Science. Michael, again, it's absolutely fantastic that you're here. I'm really looking forward to your talk on data simulation from an eventful past to a bright future, and the floor is yours.
Thank you very much, Peter Jan. This is wonderful of you, and thanks for the invitation and the opportunity. I also want to mention that actually Olivier Talagrand and myself first met while we were still graduate students at the summer school at Les Ouches, and I even co-authored a contribution of his to the proceedings of that summer school, which he mostly wrote, and in French, actually. It wasn't about dynamic meteorology, it wasn't yet about data simulation. Anyhow, so although, of course, I've worked over all these years with quite a few people, and you can find their names and the references in these places, some of the stuff that I'll have to talk about today is quite recent, and it's with Eviatar Bach, who's a MOPCA postdoc. This is a fellowship started essentially by the President Macron of France, Make Our Planet Great Again, and with Dan Krishan, who's a full professor at Imperial College in London, and I added the Imperial College logo to this first page because I really like it. And TIPES is an EU project on tipping points in the Earth system, which is quite relevant to what I'll talk about today. So this is the outline. I'll start with the data. Obviously, I'll be touching upon some of the points that already Olivier talked about, but it's might be a somewhat complementary point of view. So I'll start with the data in situ and remotely sensed, and proceed with the basic ideas of data simulation, data types and issues. So essentially how to combine data with models, transfer of information between variables, which is common to all areas of data simulation or sequential estimation or whatever, but also between regions, which is somewhat less talked about, data sparse and data rich regions. And then I'll touch upon filters and smoothers. Many of these topics that I'll only touch upon and refer you. The slides themselves will be either on the website of ISDA, or I will put them on the Zenodo website. Anyhow, it will be available within a few days, so don't take notes. You'll be able to refer to the actual slides. Then, why does data simulation work in planetary flows? This might sound a little bit unusual, but you'll see why I'm asking this question. So the geostrophic adjustment that Olivier touched upon, I'll mention, but not have the time to talk about identification or estimation of both model and noise parameters, both at grid scale and below. And in particular, the issue of the stability of the forecast simulation process, which Olivier also touched upon in the second part of his talk. I'll say something briefly about machine learning, which is obviously becoming more and more popular in all sorts of areas, including data simulation. Among the novel areas of application, I'll only touch upon two because I don't have the time for more, and conclude with some remarks and a lot of bibliography. So, main issues. Well, the solid Earth stays put to be observed. The atmosphere, the oceans, and many other things do not. So essentially, the book by Alberta Hantola, RIP, that Olivier mentioned, is based on the great progress that was done in solid Earth geophysics using inversion methods, but these do not apply as such to fields in which dynamics is preponderant. So there are two types of information. I'm using these words slightly differently from Olivier: direct, the observations, and indirect, the dynamics, which is essentially what we've learned from past observations, and these days we're trying to learn from machine learning. Both of these have errors, and we want to combine the two in an optimal way or in several optimal ways. Suboptimal, but as close to optimal as possible. So advanced data simulation methods provide such ways, either via sequential estimation, essentially the Kalman filters, and controls theory, essentially the adjoint method or methods. The two types of methods, as Olivier mentioned already, are essentially equivalent for simple linear systems. It's a so-called duality principle between estimation and control, but their performance differs for large nonlinear systems in accuracy and in computational efficiency. So you want to study, as is done today, optimal combinations of, as well as improvements upon currently operational methods such as 4D VAR and NKF. I don't have to define the acronyms anymore. So data. This is the picture from 40 years ago as presented in this book edited by Leonard Benson, myself, and Erland Schalian. The order of the editors is alphabetical because this was published. It's the only one of the so-called seminars of the European Center which was actually published as a commercially available book by Springer in an applied math series. So the order is alphabetical and it's inversely proportional to the contribution to the work. It's really Erland who was in charge of the education at the European Center at the time who put together the book. So what this particular picture shows is the sorts of observations that were available at the time of what was first called FIGI, the first GARP global experiment, and later, since there wasn't a second one, it was renamed GWE, the Global Weather Experiment, which unfortunately wasn't pronounceable. Now, the main point of this is that indeed, aside from the so-called conventional network operating at synoptic times, noon and midnight Greenwich, there started to be observations that were continuous in time, such as polar orbiting satellites and geostationary satellites, etc. The total number of observations at the time was of the order of 10 to the 5 scalars per, let's say, synoptic period, 12 to 24 hours. And if you divide that by the significant number of degrees of freedom as available via the numerical weather prediction models at the time, gave you about 100 observations per significant degree of freedom per significant delta t. And so the question arises, with all these observations, why were we doing so poorly in prediction? And why, in a sense, we're not doing that great even today? So nowadays, I haven't updated this slide. Sorry, as Olivier said, it's more like 10 to the 9 these days. But the problem persists. On the other hand, in the ocean at the time, as per the Atlas of Sid Levitas, this is not number per day. This is number of observations per month of so-called bathythermograph casts, first marine and then the so-called expendable. I won't go into the details. And this is really minuscule. If you take the ratio, it was ordered to 10 to the 4 in the past. And when I say in the future, I mean the present. It is still the case that while we have now satellite observations for the ocean, these are really surface observations. Acoustic tomography, which had held some promise for looking through the ocean in 3 dimensions, hasn't quite achieved its promise. There are now more and more drifters which do contribute substantially to it, but it is still the case that the ocean does not do as well as the atmosphere. So now there are 2 forms of data assimilation for the coupled system, essentially weak coupling with the models being coupled, but the data assimilation not, and strong coupling where both are. Okay, basic ideas, data types, and issues. Evolution of data assimilation. So this is a picture also from that book, a table contributed by Neil Gustafsson from the SMHI, the Swedish Met and Hydrological Service, and which was reproduced in this review paper with Paola Malanotte Rizzoli, which Olivier also mentioned. So what we're doing at the time, you know, which is close to the time when I became interested in this in the 70s, successive corrections and variational blending, and statistical interpolation, and so more successive corrections, and some polynomial interpolation, etc. So in the transition from early to mature, what I would call from early to mature phase of data assimilation in numerical weather prediction was, well, the Kalman filter, also contributed in that book. This paper is about somewhere between 1/3 and 1/2 of the book. And then basically variational methods, Lewis and Derber, influenced by Yoshi Sasaki, Japanese meteorologist who was at the time active in Oklahoma. And then the paper by Le Dimet and Talagrand, which actually preceded the one that was cited by Courtier, influenced mainly by the leading French applied mathematician Jacques-Louis Lyons. Okay. So what are the basic ideas in just some very simple formulas? Data assimilation and sequential estimation. Simple illustration, we want to estimate T, the temperature of this room. Well, this is a slide which was presented many times in person. So think of each one of the room that you are in based on the readings of 2 thermometers and by a linear estimate with positive coefficients which sum to 1. The interpretation in this context will be that T1 is the first guess of a numerical forecast model, and T2 is an observation, where the radio sound satellite, etc., and T hat, where the hat stands for the estimate, is the objective analysis. So if the observations are unbiased and we want the estimate to be unbiased, as I said, the coefficients have to sum to 1. That's what's also called a convex linear combination. But unwrites this in the asymmetric setting of a dynamic problem as T1 plus alpha 2 multiplying T2 minus T1, which is the update or innovation. If the T1 and T2, the two thermometers, are uncorrelated and have known standard deviations, you can define the accuracies. I learned this from Chuck Leith, who spent a sabbatical semester at Courant in the office next to mine, as the inverse of the variances, which makes the formulas look much simpler and more intuitive. T hat is T1, okay, plus A2 divided by the sum of A1 plus A2 of the update, and its accuracy is the sum of the accuracies of the observation and the first guess, and it is larger than the maximum of either accuracy, and this is the blue. Now, I will not take you through the equations on this slide, but you start with a true evolution that gives you some observations that have errors, and you do a forecast, and then you combine the forecast with the observations in the assimilation step. And this is a forecast assimilation cycle, one step, or like I like to refer to it today in the perspective that I'll try to give you as a forecast assimilation process, a dynamic stochastic process. Now, concerning the advection of information, which I find is, well, characteristic to partial differential equations applications of sequential estimation, is that there are data dense and data sparse regions. And taking this from a paper which was written at the time at which the results of the GWE were being processed, it shows you the huge difference between only using conventional or no-sat observations, where the oceans are very dirty, they have sparse observations, they are poorly known, and using this figure GWE analysis, including satellite data, in which the difference largely disappears. Here is the lack of information, which makes a contrast here, because it renders the analysis of a North America poorer. This deleterious effect disappears in the presence of time-distributed data. Now, the main products of estimation. So this actually goes back to Norbert Wiener's 1949 book. It turns out that the year 9 in every decade is an important date for data assimilation. 1949 was Wiener's book, and also the first paper by Chinese Fjodor Neumann, who were on that picture that Olivier showed. And 1951 was a Cressman paper on successive corrections. And 1971 is going to be another paper by Chinese that I'm going to show you. Okay, so here is X, the state, versus the time, starting at T0. And here are the observations, and here is where the observations stop. So you have filtering, which estimates a state at the time when you are running out of observations. There's smoothing, where you are exploiting the observations over this interval in order to estimate, to improve the estimate of the state over this interval, and finally prediction. One of the remarkable things about this thing is that there's no way that you can improve the prediction beyond having the best estimate at the end of the observations. This is non-trivial and not as widely known as it should be. So there are also parameter estimates that I won't have the time to talk very much. But I will just want to mention that one of the new applications that I'll have just one slide on is DADA, which is data assimilation for detection and attribution. And this slide, in which I was talking about distributing all this over the web to scientists and to the person in the street, said at the time, just have fun, but these days there's also not just fun, but also machine learning. Okay, so why does data assimilation work in planetary flows? So now we're starting to almost get serious. So there's geostrophic adjustment, which is in the dynamics, but should be also in the data. And, there are data distributed in time. I will not really have the time to talk about estimating parameters. So basically, this is a paper that I mentioned already. As you see here, it was, well, it was 1950, sorry, but a lot of the work was published in 1949. And the introduction says, one of the aims of the meteorological computer, I'm sorry, it's a Panofsky paper, which was published in 49 before the prediction papers. The introduction says, one of the aims of the meteorological computer project at Princeton is application of the hydrodynamic equation to forecasting. Initial conditions for this problem would be furnished by the observations at the starting time t0, would be required to know the meteorological variables and some of their space derivatives at certain grid points. This could be accomplished by a certain number of ways, and this was the objective analysis which Hans Panofsky, who also participated at this and was at the time at New York University, which is also where the Courant Institute is. Okay, so what about the satellite data that were hinted at already a few times? Use of incomplete historical data to infer the present state of the atmosphere by Jule Charney, Milt Halem, and Bob Jastrow. So this was in 1969. So one of the principal objectives of GARP is the acquisition of data which define the synoptic state of the atmosphere globally for use in long-range prediction. Since all proposed global sounding systems suffer limitations, the concept has arisen of a combination of such systems permitting trade-offs among the meteorological parameters, which really means variables, and between space and time. So if it should prove possible to obtain the large-scale wind field from temperatures alone, the timetable for the implementation of GARP might be substantially advanced. And this is what we illustrated in this paper, which also was published in 1979. Okay, time continuous assimilation of remote sounding data and its effect on weather forecast. Okay, so now I'm coming to the most up-to-date answer to that question. Why the heck does it work? You have to realize that there is no proof in the literature, no rigorous mathematical proof of sequential estimation working for anything but stable systems. In other words, everything is known about linear stable systems. A lot is known about nonlinear stable systems, but very little is known about how sequential estimation or the forecast assimilation process works for unstable systems. So again, Olivier already hinted at this work, which was largely driven by Anna Trevisan, RIP. And this is a paper from 2008. With her former student, Alberto Carrassi, now a full professor in Reading and next somewhere else, and another one of her students. And I was very honored to be a partner in this adventure. Here's an assimilation experiment, again, with a 40 variable version of this Lorentz 1996 model. And what you're seeing here is a spectrum of the Lyapunov exponents, 40 Lyapunov exponents for 40 variables. And the red is a free system, in other words, without observation. So you see that there are about 10 positive Lyapunov exponents. And then the other ones are including observations with this idea of Anna of assimilation in the unstable space with 3-hour, 2-hour, and 1-hour update, which gets successively better. So you are clearly numerically, we know that you can stabilize it. numerical weather prediction would not work if this were not true, because of course the atmosphere is unstable and chaotic, and as Lorenz said in the 63 paper, instability is at the heart of chaos, instability and saturation. So now data assimilation as a random dynamical system, which is something that I think I talked about for the first time in public at the colloquium, which was dedicated in Bologna to the memory of Anna Trevisan and her work. Recall the forecast assimilation steps of sequential estimation, okay? So what I'm referring to is what I showed you here. This is a forecast step, and this is the assimilation step, okay? And the way you can write this in continuous time with a dot indicating time derivative, I say sloppy notation because it really should have different kinds of D's for the time and for the Wiener process, but let's just write it like this. So the time derivative of the estimate is proportional to the estimate, with the proportionality being given not by A, the dynamics, but by A minus KH, where K is some set of weights, optimal or not, and H is the observation matrix, and Z are the observations, or the observation process, which is itself random. So the mathematical framework of open dynamical systems, we know of a lot in meteorology, largely due to Lorenz and others, and outside meteorology due to Poincaré and a lot of other great people who knew about chaos about 100 years ago. But what about open systems? So that was much less known until recently. It started really with a view of George Sell on skew product flows, and then came the work, the mathematical work of Crowell and Flandoli and Ludwig Arnold, no relation to V.I. Arnold, or in the physical literature, Celso-Gregori and et al., with the references here. So I will try to give you just a very, very quick view of this, of how to adapt things to the fact that attractors can no longer be fixed points or limit cycles or things which are fixed in time. Again, I don't have the time to really take you through the equations, but as I told you, they will be available, if not today, at least at some point during next week, on some website that will be communicated to you by the organizers of this setting. And the main thing is that for the deterministic systems, there is a generalization that is called pullback attractors, and in the case of randomness, they're also referred to as random attractors. And the way that this looks, if I could stand in the same room with you, I could do this by gesticulating, but basically what you are doing is you are looking at successive snapshots of something that evolves in time, and as you pull back to some compact set at initial time and you let it rip, it will converge to that snapshot. And again, you can do the same thing at the snapshot at some later time, and the only thing that is needed is that the so-called driving noise or time-dependent deterministic forcing have certain invariance properties. So the rigorous result that I was dreaming about and that Dan Krishan achieved is embodied in the following two theorems. Essentially, for now, in the presence of instability, the theorem 1, nonlinear, says if the coefficients f model, h observations, sigma, variance of noise, and the measure, so what is being estimated is what Olivier was referring to as a probability density function, okay, invariant measure in more mathematical parlance. So there's one that starts from the right initial condition, and there is another one which doesn't start from that one. And so the supremum of the expectation of the Wasserstein distance between these two things as they move along in time is bounded. In the linear case, we can actually show that it is 0. Okay, what's the Wasserstein distance? The Wasserstein distance actually goes back to Monge, who was an artillery officer and the founder of the Ecole Polytechnique, as well as accompanying Napoleon on his expedition to Egypt. And it is called the Earth Mover's distance because his problem was how to dig a trench and move it to some other place. So you can think of the invariant measure as being the dirt in the trench, and this distance being the effort required, the minimal effort required to move the dirt to some other trench. Okay? And so the paper, you can find it, you can find it right now on Archive, and there are parts of it that are written for non-mathematical audiences. Okay, so moving along, a little bit about machine learning. I know that there are people in the audience who know more about this than I do, but I'm learning from Eviatar, and so the slides are in collaboration with him. They are basically drafted and slightly by him and slightly edited by me. So use of machine learning in data assimilation. So these have proliferated in recent years. There's a application to model correction, essentially for Marc Bocquet's group. For the forecast itself, which can be implemented as an online process where the data assimilation used to provide better training for the machine learning, and the machine learning used to forecast itself variable. To emulate unresolved scales, which sometimes are thought of as this noise that I was mentioning before, and for learning the assimilation process directly. In forecasting, due to the high dimensionality, the curse of dimensionality that again you heard an hour ago, of the atmosphere and its models, hybrid models that combine machine learning forecast with physical models are necessary, as shown by a group at Maryland that includes Brian Hunt and Ed Ott, that I mentioned before. And how do you combine several models, whether high-end models of operation and NWP type, as well as data-driven models with observations for state estimation? So use multi-model DA. A single model DA is what's shown in this forecast assimilation process. You start with a forecast time t, observations. This is really just showing the PDFs that for which I showed you the graph of the process with those rectangles. Okay, and this gets this weight, and the other weight gets that weight, and you get the analysis, apply the model, etc. This you all know. Here you have multiple models that have maybe of totally different nature, as I said, really high-end or relatively simple, and with different state vectors and different resolutions, and you combine those, and then you apply the analysis again to all the models, and you proceed like this. This just says the same thing with equations, and again, the paper is on Archive, submitted just a few days ago. So here you have the list of references. I won't dwell on it because you'll have it when this is online. Okay, novel areas of application. So I will just touch upon two of these, and again, in a very summary way. Again, when I said 2 decades ago, that was also a decade ago when I first had this slide, I believe. There were really just a few satellites up there. Actually, this institute that I was running at UCLA had a fairly large space plasma group, and they had an instrument on each one of these satellites. And now you have space platforms and clusters of satellites in Earth's magnetosphere, so stuff is much more exciting. Let me just show you a quick, since I'm doing pretty well on time, let me show you a little movie because I find that very illustrative Okay, it's from DARC, Data Assimilation Research Center at Reading, which Bill LaHose was running at the time. And it shows you ozone at 10 hectopascal, or millibar if you prefer. And the color refers to the ozone concentration at that point in space and time, being high or low. And this is the result of the forecast assimilation site. So the satellite is NVSat, and this is the result of the forecast assimilation cycle. And now I'm just going to run it. Okay. So you'll see that as this satellite, its orbit moves around, it updates the assimilation map, okay? And it will eventually converge to something that is, you see that these two holes in the ozone are filling up in time. Okay, gotta stop it, although it's fun to discuss further because I have to go back to the slides. Okay. Okay, so the other one is fascinating, and again, it was originally the idea of Alexis Anar to apply data assimilation to detection and attribution. And we had a meeting he was at the time in Buenos Aires, and we had a meeting at the Academia de Ciencias of Argentina. And from that moved on to a French-funded project and a couple of papers that also involved Alberto Carrassi and Marc Bocquet, and the first one of which is published in the Bulletin of the American Meteorological Society. So here's your observed forcing. Again, this is essentially non-autonomous or random dynamical system problem. Observed forcing, natural plus anthropogenic. Evidence of causal links. Here's your observed system behavior, temperature, precipitation, trends plus events. And you want to tell to which extent the anthropogenic forcing participates in driving the mean and the additional extremes. So the idea was to use this rather counterintuitively named counterfactual theory of Judea Pearl. I mean, Judea Pearl is a computer science, informatics in European language professor at UCLA, whom I knew personally, and who got the Turing Medal, which is sort of the Nobel Prize of Computer Science, for this theory. And basically what the theory does, as opposed to what is usually done in this field of detection and attribution, is that it determines necessary and sufficient conditions, which is not quite the same as frequentist analysis, etc. But I can't say anything more about this because I would like to proceed to the concluding remarks and sort of projections of future work. So computational advances were enormous in this time. Hardware, more computing power, CPU throughput, larger and faster memories. In terms of software, better numerical implementations of algorithms, automatic adjoints for the control theoretical methods. Olivier mentioned sparsity, block-banded. Basically, block-banded matrices are the same thing as localization. And we had worked on that with Steve Cohn a very long time ago, but okay. Reduced rank and other sparse matrix algorithms. Better ensemble and particle filters, including localization, efficient parallelization, etc. So how much data assimilation versus forecast? Olivier already mentioned that today at European Center, 40% of the computational effort is in data assimilation because essentially you have to do something about the PDF or about matrices rather than vectors, whatever you do. So in principle, it would be best to design integrated observing forecast assimilation systems. but that's not how the world works. The observing systems, OSSIs or not, in other words, observing system simulation experiments, which were started for GARP, are not really what produces the instruments. It's the engineers and other needs that produce the instruments, and you got to work with what you got. So observing system design, in principle, you need no more independent observations than the degrees of freedom that need to be tracked. So as feature here, just some examples, obviously with some preference for my own junior contributors. You track features, Lagrangian data assimilation. The issue of instability is, well, the major contribution was that of Anna Trevisan and her students, but actually we had looked at that with Ricardo Todling somewhat earlier and shown that in a certain simplified baroclinic instability problem, it suffices to use one well-placed observation which captures a growing baroclinic instability. Trade-off between mass and velocity fields, well, I told you about Charney and associates, etc. So here you have this assimilation in the unstable space by Trevisan and colleagues, plus rigorous math results, which I cited already, which we just obtained with hard work of DANS over the last 2 years. The cost of advanced data assimilation is much less than that of instruments and platforms. At best, use data assimilation instead of instruments and platforms, but that's of course a joke. At worst, use data assimilation to determine which instruments and platforms, advanced OSSIs, so at least between certain proposed instruments, you can decide further funding for some and not others according to this. Use any observations if forward modeling is possible, the observing operator age, satellite images, 4D observations via machine learning, pattern recognition observations, and in phase-based statistics, again, machine learning. Conclusions. Theoretical concepts can play a useful role in devising better practical algorithms and vice versa. That was sort of the credo of the Courant Institute, that there are lots of problems that you can do, but some need to be done and others can be done. Okay, so theoretical concepts can help, and you can decide on which theory you do depending on what the practice requires. So judicious choices of observations and method can stabilize the forecast assimilation cycle. Some examples in the paper with Dan clearly support that. Trade-off between cost of observations and of data assimilation. Assimilation of ocean data in the coupled-array system is useful. That wasn't always clear. Strangely, there were people who thought that it makes no sense to observe the ocean itself. They help estimate both ocean uncoupling parameters, in other words, fluxes at the ocean surface, which are very important for the climate. Changes in estimated parameters compensate for model imperfections. That's again something that I didn't have the time to talk to you about. But if you have some sort of a simplified model, which does not, for instance, simulate ENSO perfectly, parameter estimation for that model can greatly improve the forecast using a such simplified model. Well, another great progress is things like, putting efforts in common via things like DART, Data Assimilation Research Testbed. So this is something that I call the DA maturity index of a field, because there are many fields to which it is applied now. Pre-DA, few data, poor models. The theoretician says, science is truth, don't bother me with the facts. The observer, experimentalist, says, don't ruin my beautiful data with your lousy model. I can tell you that when data assimilation started in oceanography, there was a lot of that going around. Early data assimilation, better data, so-so models, stick it in the observations, direct insertion, nudging, advanced data assimilation, plenty of data, fine models, and EKF via 4D VAR, unscented Kalman filters, particle filters these days, what I call post-industrial DA satellite images directly into weather forecast and climate movies. And again, we've come a long way in 60 years. Some advances are laborious and incremental, e.g. sequential. You know, there used to be a couple of decades ago fairly animated discussion about sequential versus control theoretical. Olivier showed you, some experiment which showed that for same effort, they do the same thing. Well, one can continue this discussion, but that's not really what's interesting. What's interesting is how to best combine them, but others are fresh and exciting. So latter include new areas of application, again, biology, geomagnetism, paleoclimate. Again, I didn't have the time to talk about that, but, proxy data like delta O18 and delta carbon 14 and things like that are to paleoclimate what satellite data are to numerical weather prediction. They can be turned into temperatures and other interesting things about climate. Space physics, I showed you a little bit of that. Data assimilation for the detection and attribution, as well as novel methodological challenges, multi-scale and multi-model problems, various forms of machine learning, inverse problems for evolution equations. Again, Olivier also mentioned that, including climate simulation and sensitivity studies, and in particular, uncertainty quantification, which is these days a big area. There are journals which have uncertainty quantification in the title, and it's clearly of the essence in policy decisions about socioeconomic impact, etc. So technological advances both pose new problems, massive data sets, higher resolution, and help solve them. Overall, it's a brave new world in which data and models actively speak to each other, and we do so to both. So enjoy. And here's one cartoon out of the New Yorker. Miss Peterson, may I go to the bathroom? I can't assimilate any more data today. And then I have a lot of references, and I think I will stop here. Thank you very much. I'm ready for questions. If you wish, just to tell you that there are many more references. The two that I was mentioning in particular as being quite fresh are these, and they're on arXiv. Okay, so I'm available for questions.
Thank you, Michael, and I give the word to Nora. So
Yes. Yeah, there's already or there are already two questions from Dan Christian. One is for the satellite data assimilation application, is the satellite data assimilated one track at the time or several at a time?
Sorry, what exactly is the question?
The question is, for the satellite DA application, is the satellite data assimilated one track at the time or several at the time?
That's a very good question, Dan. There are various ways of doing that. I mean, it's not one track. It's basically at a certain time step of the model. Okay, what I showed you, that dark movie, was done on purpose to see the impact of the satellite data on the forecast assimilation cycle. But what is assimilated is the data at a certain moment in time. And well, let me see whether I might be able to find, I might be able to find a picture out of that paper, the Ghil Atlas paper, that shows such a picture of what exactly is assimilated at a certain moment in time. But it might, here's old reprints. Okay, sorry, too many papers. Here, okay, got it. Wonderful. Okay, let me just step through it and then I'm going to magnify it. Okay, here is a picture of what we called at the time a satellite data patch. Okay, So the TTTs are actual data from satellite. You know, satellite doesn't just look straight down. It looks also sideways. It sort of sweeps. And so this is a patch of the influence function of such a satellite data patch. Okay, but there is a point which we worked on at the time with Steve Cohn, and it is mentioned in the review 1991 review paper with Paolo Rizzoli and has been exploited more recently. It's the idea of processing incoming data in steps. Okay, so again, this gets into details. If you'll allow me, I'll tell you the rest of it, Dan, in person the next time we meet online, which is not next Friday, but the one after that, as you remember.
So thank you, Michael. There are more questions in the OPED. Some people are very impressed by your productivity and what you did in recent years. And there's, I will read the question by Lars Nerger, and he's mentioning, so you didn't comment a lot on nonlinearity. What do you think is the challenge in this direction? So
I didn't comment on what?
Nonlinearity. So what do you think are the challenges?
Nonlinearity. Well, everything that I talked about is by now nonlinear. I mean, nonlinear and chaotic, and that's exactly the point of the work that we're doing with Dan, and where we're already thinking about follow-up, because there are a number of ways. I mean, as I say, practice inspires the theory that you want to do, but also the theory can inspire the practice. The fact that quite clearly this sort of gives the blessing of mathematical rigor to the idea of concentrating on the unstable space is one thing. The other one is the fact that expectation that I showed you, no, not this one. Okay, here. That expectation that I talked to you about. Okay, where in the world? Yes, here. I think. Yes. Okay. You see, this expectation that I mentioned here extends over the randomness of Z, of the data. And that is not always taken into account. In principle, one refers to so-called deterministic ensemble Kalman filtering, in which you ignore the randomness of the data, and stochastic, where you do take it into account. Obviously, taking it into account looks more expensive, but then you have to suffer the collapse of the ensemble, which I don't think Olivier talked very much about. And so people use artificial inflation of the variance of the ensemble. Instead of using artificial inflation, you might recall to take into account the randomness of the observations again, in a judicious way, using some form of smart sampling, okay, in order to maintain the natural variance of the ensemble. So everything is nonlinear by now. I mean, I didn't specifically mention that. I only mentioned here that at this time we can prove not just boundedness of the error in Wasserstein distance, but actually it's tending to zero in the linear case.
Thanks. So I see that we are a little bit over time already, so I need to ask Nora, do you think we should do another question, or should we, or Michael, do you have time to answer some questions?
I can answer. I started a little bit late by no fault of mine.
No, I know. It wasn't your fault at all. So so I would say then we wrap up now your talk, and I want to thank you and also Olivier for preparing your presentations, giving them today. We really much enjoyed the talk. And yeah, so I would say thank you again.